Didn't make sense.
So, I know you're all probably brokenhearted about it. We'll have a substitute on Friday as a calculus challenge. But we will have class. So I want to talk about linear independence of automorphisms. Let S be a non-empty set of automorphisms. It'll F. It's non-empty set of automorphisms F. We say that this set is linearly independent if like say AI and F, this is of course finite. And automorphisms in F. Sigma S. Then the relation sigma I U. So if the Hadwick relation holds for all U and U, sorry, for all U and F. So if this is what we mean, say that a collection of homomorphisms F are linearly independent, if basically this is AI sigma I 0, that means their evaluation is 0 for any U and F. That means that all the coefficients are 0. Lemma. Step 4. Any set of distinct homomorphisms. F is linearly. So there's kind of a low bar there, that all you need for linear independence is that they're distinct. If not, then there exists non-zero AI and F and distinct automorphisms such this holds. Zero. Sigma I and S such that AI sigma U is equal to 0. Now we're going to kind of pull the trick here. We're going to assume that this is a minimal such dependence relationship. that is among all U's where such a dependence relation does exist. We find the U that minimizes N, and this is my linear, this is my minimal relation. Note, N must be bigger than 1. All right. So since all the automorphisms are distinct, there exists V and F such that sigma 1 V and sigma 2 V differ. Well, it's not the case, of course, sigma 1 and sigma 2 would have to be the same automorphism. So let's apply this let's apply this automorphism or apply this element let's apply this equation to UV. And what do we get? And I'm going to liberally use the fact that this is an automorphism. A1, sigma 1 U, sigma 1 V, plus A2, sigma 2 U, sigma 2 V, plus AN, sigma NU, sigma N V is 0. So this is where we apply that equation for that, right? Apply that equation to the element UV. We can also get something similar by multiplying that equation by sigma 1 V. And what this is going to give is, instead of replacing this with UV, I just multiply that by sigma 1 V. This gives me A1, sigma 1 U, sigma 1 V, plus A2, sigma 2 U, sigma 1 V, AN, sigma NU, sigma 1 V, 0. Now, let's subtract these equations. First. Take this one and subtract this one. Let's see, this minus this. Notice, of course, the first terms cancel out. All right. And so we kind of pick this up at the second term, and this is going to be okay. A2 sigma 2 U, it's a common, and that's sigma 2 V on sigma 1 V plus three sigma 3 U sigma 3b on sigma 1b all the way out to a n sigma n u sigma n b on sigma 1b. So notice, perhaps I should write this way. Sigma 3b and sigma 1b. And sigma b. And notice this thing is not zero because of our assumption. So now with these larger coefficients here, notice these things here are just numbers, right? This fixed b. And notice we now have a smaller dependence relation. This contradicts minimality of perfect equal. And so, since there is no such dependence relation, we have that this is a linearly independent set. Let me give you a definition. Oh, interesting. Stand on. Okay. Definition. Say the extension of the K. So let's field extension K is cyclic respectively abelian if F is Galois K and Galois group that open K is cyclic respectively abelian. In fact, we know of a large class of cyclic extensions, namely any finite extension of finite fields. Right. The Galois group in that case is always cyclic, and of course, any extension of cyclic is abelian. Anybody give an example of an extension that's abelian but not cyclic? You might try looking at something like Q adjoined with square root of 2n squared. I believe that one is Z2 sum Z2. Okay, so here's a theorem that's really kind of, in fact, this is sort of fundamental for the basis for a lot of interesting stuff in number theory, field theory, Galois theory. Of course, it is squeezed into a pretty It's pretty rarefied circumstance. Theorem 876. Let F be cyclic over K, so I'm on cyclic extension of degree N. We'll say degree N. Degree of F over K is N. Galois group is cyclic, so isomorphic to C N. Will sigma be a generator of the Galois group and U and F? Sigma and so U is an number one, the trace U is 0. So the trace of this element is 0 if and only if U is equal to B minus sigma B for some B and N. By the way, with both of these things, I'm going to give you one direction that's very easy. The other one is the interesting one. It'll be very easy to see that if U is of this form, V minus sigma V, sigma is generated Galois group for some V and F, then the trace is 0. The fact that any element of that trace has to be of this form is more interesting. And two, this is famously called Hilbert's theorem 90. And it's the analog of this in the multiplicative case. The norm of U is equal to 1 if and only if U is the form V sigma V inverse. I don't think these tips are incredibly hard, especially once you see what to do. But let's check old Jim on the details. You got to be a little careful. Suppose what is the trace of U? And in my proof, I'll suppress these subscripts and superscripts here. This is sum I1n sigma I. Right? But this is the sum sigma I of D minus sigma V. Now remember, these sigma i's, they're all homomorphisms, right? So this is So let's write this down separately. This is all, this is, well, think of it, this is sigma 1V, and you subtract, one is kind of backwards to start with. But notice that when you put in here, this is sigma the n plus 1V, which is sigma 1V. So that cancels. When you have 2 here, it's a sigma 2V, it's canceled by the first term here. Basically, the sigma i's cycle through all the elements of the Galois group. They're all applied to V, and this is just the same set of things shifted. Add, subtract. On the other hand, let's suppose that you have an element that has trace 0. We choose an element, let's choose W and F such that the trace of W is 1. And let me first assure you that you can actually do this. The reason you can do this, since the automorphisms here, of course, is the Galois group is cyclic and is order n. These are all distinct automorphisms. We've proven that if you have a collection of distinct automorphisms, they have to be linearly independent. So there exists Z and F such that Z plus sigma Z plus sigma squared Z plus sigma n minus 1Z is not equal to 0. Right? Because of the linear independence of the automorphisms. So in particular, what this equation means is for this particular element Z and F, the trace of Z is not 0. So let W equals 0 for trace of Z. Okay. By the way, everybody okay with the fact that the trace of this is, notice that the trace of Z, this element itself, is unaffected by any element of the Galois group, right? So this is actually the base. So if you take the trace of W, it's going to be the trace of 0, the trace of Z, which is 1. Right. Okay, so now we've got our element W of trace 1, and we're going to use that as follows. Let's let V equal UW plus, let's see, go on the pattern here. U plus sigma UW U plus sigma U plus sigma squared U sigma squared W. So pattern it out like that, all the way up to n minus. U plus sigma U plus sigma n minus 2 U sigma n minus 2 W. Now, if we want B minus sigma B, let's look at B minus sigma B and see if we can compute this. Well, right now, this is super just already line. This is U W plus, that is. Okay. I claim that that is what you get when you take V minus sigma B. Let's take a closer look. I don't want to just, you guys can figure it out, but I want to take a closer look at this. V is this thing. Look at sigma B. This is sigma U, sigma W, plus sigma U, sigma squared, sigma U, plus sigma squared U, plus sigma cubed U, sigma cubed W, plus sigma U, plus sigma squared U, plus sigma n minus 1 U, sigma n minus 1 W. So what happens when you subtract this? Let's take a look. See if we can get to the top of this conundrum. So if you look at V minus sigma B, so in other words, this minus this, well, sigma UW, agreed? There's UW. Then you get this mess. Let's see, this is oh, right. So my U sigma W comes out of this first one. And U sigma W comes out here. Sigma U sigma W is subtracted off here, right? Now, so I've got this one. Then I need this guy. Well, it comes from subtracting, so I need U sigma squared W. It comes from the first term of this, Notice that the second, what's left over in this term is sigma u sigma squared w, which is here, and then sigma squared is, so you cancel this, right? Everybody see how this pattern works? And this persists all the way up to the n minus one term. Everybody okay? So what do we have? We have b minus sigma p is u times whatever that mess is, w. So
What happened with the last term is sigma to the n minus one?
the trace is zero, right? So, yeah, I should have said something about that. That was our assumption in the first place. So sigma n minus one, u is the sum of all conditions. Well, minus. So yeah, I should have said something about that. This is u times w plus sigma w plus sigma squared w. And how far can we go? Sigma to the n minus one. But this is the trace of w. It's been constructed. And so we've got the direction. A minus sigma b is u. Okay, Hilbert's theorem 90, the multiplicative analog is very similar. It's theorem 90. Two. Yeah. Is equal to E over sigma b. Then normative is the product sigma of b over sigma b. So it should be sigma I. And this is the same mess we had last time. This is the product sigma I b sigma I plus one b. So basically, this is sigma one, sigma two, sigma three, all the way up to sigma. Sigma n gives you the identity, so this is the product of all these. This is the same thing, except now it starts at sigma two and ends with sigma one. Right? So this cancels. So once again, that's kind of not too bad in that direction. In the other direction, as you might guess, you set up kind of a similar thing that you did here, only you do the multiplicative analog. So we went through and selected a particular element. Here we do a multiplicative analog. on direction, we find a y in F such that V y plus sigma u sigma y. This will establish the pattern. Finish off this. Sigma u sigma m minus one u sigma m minus y. Find a y and f such that this mess is not zero. Just like we did before using linear independence. Now verify that if you have u inverse times v, let's see. I think it's exactly. Yes. So I'll leave that one as an exercise, kind of fun to go through this. Remember, recall. Here's something I have to do. Recall, if you do this, the norm of u is equal to 1. So u sigma squared u sigma n minus 1 u is equal to 1. That will be useful, just like the trace of zero is. Now I'm dying to give you a kind of a neat example that demonstrates an application of Hilbert's theorem 90. And some of you may have seen this, like in a number theory class, or maybe in some other context. It's classical. Hilbert's theorem 90. Consider considering Q inside of QI. We know from class that this is an extension of degree 2 and characteristic 0. So it's Galois group Z2. So it's cyclic, right? So Hilbert's theorem 90 would apply in a rather easy case. This is a cyclic extension. Its Galois group is generated by here. My sigma that generates the Galois group is just the complex conjugation. Now let's suppose that we have rational numbers a and b, and its norm is 1. So suppose I have two rational numbers and suppose that their norm, the norm of A plus BI is 1. This is the element in the Gaussian rations. Hilbert's theorem 90 says that this element, my U here of norm 1, must be of this form. So let's see what we can get out of that. So say here, this is what the plot is. So this is actually A and B are a pair of rational numbers that are a solution to this equation, right? So it must be the case that A squared plus B squared is 1. By Hilbert's theorem 90, there exists C in QI such that this element A plus BI is 0 C. Which in our case these have some common denominator, so we can assume that these things, we can clear the denominators, assume that both x, y are in fact integers. And this is where a little number theory part's going to come in, right? So A plus BI must be this, but now we've got x and y being integers, I can clear the denominators. So now when we go back to high school, we can rationalize this, whatever we call it back then. And I get A plus BI is equal to multiplying top and bottom by x plus IY. I'm going to get x squared minus y squared plus I times this 2xy. Right, okay with that? So this actually gives that equating coefficients and this is actually, how many of you have seen this parameterization of rational points on the circle? So if you have like A and B being rational points on the unit circle, you can actually parameterize what they are this way. This is also a way that you can get Pythagorean triples out of this. And all that comes from this observation with Hilbert's theorem 90. Okay, any questions? Um, with this in hand, I'm going to take a quick look at cyclotomic extensions. Just to kind of expose you to it a little bit. So definition. We say that for the unity. Well, the power of this one. What are you supposed to primitive means? Right, no lower power. Well, let me check you on this. Well, maybe aware of primitive inference of unity on the circle. So if this is the complex plane. Well, let me state this way. So you might have seen this in other contexts, right? If you look at e to the 2 pi I over n, notice that when you take the nth power of this, you get e to the 2 pi I, and no lower power works. By no lower power is 1. How many of you have ever seen this, like, you know, so for example, if you have, let's see if I can stop right. These are the primitive. But that's, in some universe, that's supposed to be like, but anyway, that's supposed to be what it does, right? And so the primitive inference of unity sit regularly spaced on the engon, right? And you've got kind of different things that happen for even and odd, right? Because, for example, if this were even instead of odd, you would actually get -1. There's, you know, sometimes you get I and make by depending on if it's a multiple 4 or not. But of course, you can do primitive inference of unity over other fields, right? Because this definition isn't field dependent. You're going to run into problems. Well, you're going to run into subtleties if your n is not relatively defined to characteristic, right? For characteristic 0, like for example, rational complex numbers, this is all good, right? But for example, if you take the field of 2 elements, what happens if you try to find a primitive square root 1? This unfortunately is x minus one squared. I'm not understanding how. I didn't know one of you guys sit on the turn on the middle of the video. I completely lost my marbles. Anyway, so that's what a primitive infinity is. We'll talk about this more next time. Any questions? All right, well, you have a good one, and we will see you. Well, somebody else.